All right, time to go teach. Hello and welcome to this next episode of Tutor Tutors, continuing looking at the cell and looking at how a cell maintains homeostasis. Specifically today, we are going to be looking at osmosis, and this is the first of a two-part series on the movement of water, because that's what osmosis is. So, targets of the day, first off, we're going to have to look at how water actually exists around the cell, and that means that we have to understand what a solution is, because water isn't typically going to be pure 100% water, and so there's going to be more components, and that means we are going to have a solution. Next, we're going to have to look at how we actually compare those different levels of tonicity, or in other words, how we measure the concentration of the water in our solution, or how we compare the amount of water in our solution. So, let's get started. First things first is we have to remember that a cell's external and internal environment is aqueous in nature, and that means that there is water present inside and outside the cell. The cell is surrounded by water, and it is filled with a lot of water. The water moving is going to have a very, very large impact upon how that cell is able to maintain homeostasis and how that cell is just flat out going to live. So, we need to pay attention to how that water moves, and that process is called osmosis. Osmosis is the passive transport of water, and you should remember back from the previous lessons that the passive transport of any substance always means it's going from a concentration that is high to a concentration that is lower. So we're moving from a high concentration to a low concentration, and that movement of the molecules requires no energy when it goes in that direction, and so that's why we call it passive transport. When we're looking at this, that means we have to understand that this water that would be inside and outside of our cell would typically be in what we call a solution. A solution is made up of two parts. We're going to have the solute and we have the solvent. So if we take a pitcher of water and we pour it into this cup, well, that would be our solvent. The water would be the solvent in this case. And if I took now a salt shaker and actually just, shook a little salt into my water, the salt would represent the solute. And the reason that the salt represents the solute is because it is going to get broken down into smaller components. The water is going to pull apart the different ions that make up that salt, and so it's going to pull those particles apart, making them smaller and smaller and smaller. And that is what dissolving is. So the water, which does the dissolving, that would be the solvent. The thing that is dissolved, the salt, would be the solute. And the combination, the salt water, that would be our solution. And the solution, the way we measure it is based upon the amount of stuff dissolved in the solvent. So we are going to be paying attention to the amount of solute that has been dissolved. What is the concentration of our solute? And by knowing the concentration of our solute, we will then be able to determine which direction water will go based upon that factor. One thing to be aware of when we're talking about the three different levels of tonicity is that they do not exist by themselves. Each of these levels is a comparison term. A hypotonic solution does not exist without a hypertonic solution. Because these are comparison terms, we must always have multiple solutions that we are comparing, at least two. And this also means that when we are comparing these two different solutions, that one solution will be described using one term, and then the other solution will be described using a different term. For example, if one solution is hypotonic, that means it has a lower level of solute. Well, what's it have a lower level of? Well, it would have a lower level of solute than the other solution that you're comparing it to, which must have a higher level of solute because it has more solute present or a higher concentration of solute present, and so it would be hypertonic. If you have a hypertonic solution, you must also have a hypotonic solution. They are always going to be linked. one solution having a higher solute concentration, the other solution having a lower solute concentration. That is the way it will always work out. If both solutions have an equal solute concentration, then they would be described as being isotonic to each other. Each of the solutions would be isotonic. And so that is the way that we would always have these different comparison terms. That's how we describe our different solutions. What's this look like in a practical way? Well, if we were to take this device, it's called a U-tube, and the reason why we call it a U-tube is very simple. It is a tube, it is a glass tube that happens to be in the shape of a U. And in the middle, there happens to be a semi-permeable membrane. And this semi-permeable membrane would allow water to pass through, but would not allow for all different solutes to pass through. So you can make it so that the solutes that you put on one side cannot pass over to the other side. And if we were to fill this with water, then this water, right now we have 100% water. That's an equal concentration on both sides. They would be, both sides, dynamic equilibrium because the water will be able to pass through this membrane equally in both directions. And it would pass equally in both directions because it has an equal concentration on both sides. But if we were to add solute to this, and we were to put solute on the left and solute on the right, now it matters how much solute is present. In this case, as it turns out, they have an equal amount of solute and they have an equal amount of solvent, so there's an equal concentration on both sides, and that means that both sides would be isotonic to each other, and the water would continue to be at dynamic equilibrium, passing in both directions equally. But if I were to add some solute to one side, now I added more solute to the right side. So that means that since I have lower solute on the left and a higher solute on the right, that means I can describe these as being hypotonic and hypertonic, because hypotonic means it has a lower solute concentration. Hypo means below. So since that side has a lower solute, or below that the other level of solute, it is called hypotonic. Hyper means above or up, so it has more solute in it. It has a higher solute concentration. So we have less solute on the left, more solute on the right. But that also has a consequence upon our concentration of water. Because our volumes are equal of water on both sides, that means there's more solute here. That means that there is less space for solvent, which means I would have less solvent there. I would have a lower percentage of solvent on that side. And over here on the left side, I would actually have more solvent present. I would have more space for that water to be. And so if it has low solute, it also would have a high solvent. Consequently, the hypertonic side, it has a high solute, and that means it would have a lower concentration of solvent. And osmosis results in the movement of water from that high concentration to that lower concentration. And so the water is going to move from the hypotonic side toward the hypertonic side, raising the hypertonic side until we reach equilibrium, or until gravity pulls the water down so it can't raise up anymore. But if the water is able to reach it, it will reach dynamic equilibrium just like usual. It will equal out the concentration of water and the concentration of solute on both sides. That is very simply the way that water will move. Water will always move from that high concentration to that low concentration, and the way that we measure it is using the tonicities. So, in summary of all of that, as we just said, the passive movement of water, it's osmosis, and that's only for water. So you see these different jokes that go around and say people talking about studying by putting their textbook underneath their pillow, or that they just sleep on it, and they said, I'm going to take in all that information via osmosis. Osmosis is only the movement of water. If somehow the information in the book could move into your head, that would be diffusion. It would not be osmosis, because unless your book is made of water, that's not what it is. And next, the way that we actually describe the concentrations are based upon the solute. which can get confusing because we're typically talking about the movement of the solvent. And so when we think about this, we have to remember that when we're talking about the tonicity, we are referring to the solute concentration being either higher in one side, equal on both sides, or lower on one side. And if the solute concentration is any one of those, that means the solvent concentration is the opposite. If we have a hypertonic solution, that means we have a higher amount of solute in that solution compared to the other solution. But that means it has a lower amount of solvent in that solution compared to the other solution. The other solution would be a hypotonic solution, a lower concentration of solute, but a higher concentration of solvent. Or we end up with equal concentrations of both solute and solvent in both, and that would be isotonic. Well, that's it for this time. Be awesome, stay awesome.